IBC Calc, these are the day 4 notes in your packet, and you'll notice right away at the top we have a warm-up. I want you to try these 2 questions on your own, kind of like we've seen in some of the other lessons here where there's a warm-up to get started. So I'll go over these with you in class the next time that we're together, but go ahead and try these 2 questions right here, numbers 1 and 2. For parts A and B there, make sure you answer those. And then we're going to jump right to the bottom of this page and talk about limits involving infinity. We've actually talked about this a little bit already, so to consider what's happening for something like the first example, the limit as x approaches 2 for 1 over x minus 2. When I plug 2 in algebraically, we get 1 over 0, which I want you to be a little bit cautious about. It seems like it's an undefined value, therefore the limit does not exist. That's not necessarily always the case. We might want to check out graphically what's happening here. So for 1 over x minus 2, we know that this function would have a vertical asymptote at x equals 2. To the left of 2, we get this branch of the hyperbola. To the right of 2, we get this branch of the hyperbola. So we can analyze this by saying that the limit as x approaches 2 from the left of this function, as I approach 2 from the left, we're heading towards negative infinity, down forever. And then meanwhile, the limit as x approaches 2 from the right is going to head up towards positive infinity. So altogether, we would say for this example that the limit as x approaches 2 does not exist. Okay, the left and right hand limits certainly do not match, and therefore the limit does not exist. So is that true for number 2 as well? 1 over the quantity x minus 2 squared? Well, hopefully remember that this one looks a little bit different. We still have that vertical asymptote at x equals 2, but this is what I refer to as being like that volcano graph, right? When you square all those negative y values down here, they're going to turn up and become positive y values. So in this instance, the limit as x goes to 2 from the left is positive infinity now. And the limit as x goes to 2 from the right is also positive infinity. So the conclusion is, if we're approaching the same infinity from the left-hand side of 2 and the right-hand side of 2, then the limit as x approaches 2 in general for 1 over x minus 2 squared is infinite. So a couple different instances of limits involving infinity. Here's an example of a limit as x approaches a value where the limit is in fact infinite. We're going to look at some other examples in the notes here if we turn to the next page, where now we're taking the limit as x approaches infinity. So for this first example here, we have the limit as x approaches infinity for a somewhat complicated looking function. And what I'll have you remember is that when we take the limit as x approaches a sum of 2 functions, that's going to equal the sum of the limits. So it might benefit us to break this down to the limit as x goes to infinity of sine x over x plus the limit as x goes to infinity of 5x squared minus 2x over 2x squared plus 1. All right, so that first part's looking real familiar, isn't it? The limit as x goes to infinity for sine x over x, isn't that 1 or something like that? And the answer to that is, sorry, it's not 1. Isn't that the world famous limit though, Mr. All? Sine x over x? Well, it's only world famous if it's the limit as x approaches 0. So I'm sure as some of you are writing this down in the notes, you're like, yep, got a 1 there, but you have to be cautious. This is not 1. Okay, limit as x goes to infinity for this is actually 0. So why is that the case? Well, let's kind of analyze this. Sine x on top, as x gets bigger and bigger and bigger, this is oscillating, right? So this is going to go between -1 and +1, and -1 and +1, and I can't decide what to do. Meanwhile, the bottom's just getting bigger and 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 bigger. So the bottom's growing kind of without end here, whereas the top is oscillating. So as x goes to infinity, the value of this fraction approaches 0. All right, meanwhile, what's going on for the limit as x goes to infinity for this rational function? Well, the main idea behind a limit as x approaching infinity being a concrete value, having an actual value and not being infinite in itself, is if you have a rational function, is there a horizontal asymptote in this case? And maybe you're recalling from those good old Algebra 2 and pre-calc honors days, that when you have this equal heavy rational function, the x squared over x squared, as x goes to infinity, the top and bottom are going to grow at approximately the same rate. So what's going to happen is it's going to equal the ratio of those coefficients out front, which is the 5/2. So now that we've broken this down into these two distinct cases, you can analyze those limits individually and get that 0 plus 5/2 would be a final answer of 5/2. You can definitely confirm this on your calculator. If you were to go ahead and type this into y1, and all you're going to do is ask for very large values of x. We've done that ask feature trying to approach a specific value of x, but for x going to infinity, pick 100, 1,000, a billion, whatever you want to pick, and you'll see that we are getting closer and closer to 2.5. And by the way, the same rule would apply for those limit combination theorems if this is a difference, a product, okay? Even the quotient would work here, right? So just keep in mind that we can apply any of those limit combination theorems. The next couple kind of will have a similar feel to them. It's the limit as x goes to infinity. In this case, for sine of 1 over x. So if we take a look at this, we're going to use a little bit of a substitution process here to help us figure out what's happening in number 2. So if you think about this, as x goes to infinity, what's happening to the value of this fraction is it's getting smaller and smaller and smaller and smaller and heading towards 0. So the way that we might be able to analyze this is actually by doing a quick let statement. Let's let y equal 1 over x. And if y equals 1 over x, we've determined that as x goes to infinity, what's y going to do? Well, as x gets bigger and bigger, y is getting closer and closer to 0. So we can actually change this whole problem right here to not the limit as x goes to infinity anymore, but we can replace it by saying, let's take the limit as y approaches 0. Remember, y equals 1 over x, so we can say for sine of y. Now, one quick note is that as x goes to infinity, y is going to 0, but it's approaching 0 from above the x-axis. So we might want to just put a little plus there to indicate that. Okay, you'll see that commonly written, that it's technically this sided limit now. As x goes to negative infinity, we'd be approaching 0 from below it, so we might put a negative in that space. So the limit as y goes to 0 in this case is going to be sine of 0, and sine of 0 is in fact 0. So the correct answer to number 2 is 0. And if we look at the next couple of examples, there's, again, that really similar 1 over x quantity that we're going to replace. So if you look at this case, we might say that for cosine of 1 over x, if we let y equal 1 over x again, I won't write this in the last one, but as x goes to infinity, we have that y is approaching 0 from above. So this becomes the limit as y approaches 0 of 3 plus cosine of y. So when I now substitute in 0 here, we